Okay, we're going to do a heap sort. So there's something called a binary heap. Now, a binary heap is it's simply a binary tree with some additional properties. So it's a binary tree, but don't get confused with a binary search tree, which is a different thing, right? A binary heap is a binary tree with the following properties. It's always fully filled, okay? And in the case of a min heap, there's also a max heap, which is sort of the inverse of this thing. But in the case of a min heap, the parent node is smaller than both its children. Okay, so we call this a semantic property here. This parent is smaller than both its children. This is a different semantic property than a binary search tree, okay? So because it's fully filled, it's efficient to use an array to store these guys. So the first layer, if you had a tree that looked like this, it's the root would be on the first layer, and the BC here would be on the second layer. Then there would be 4 elements here with indexes 3, 4, 5, and 6, and that would contain the other guys. So for a fully filled tree, an array is an efficient storage technique. And if you're using an array, then you can use these indexes here to move up and down in the tree. You can move both ways. We have these formulas. The left child is 2n plus 1. The right child is 2 quantity n plus 1. And the parent is n minus 1 over 2. This is using these index, like 3's parent is going to be B here. 3's parent is 1, so D's parent is B. If you work out this here, and you can go up and down between B and D using these formulas here. So, so we have some rules for doing insertions. So you always insert at the last position. So that's going to be the end of the array. Okay, and so you just fill the array from bottom to top, which sort of corresponds to a left to right, bottom to top thing in the tree. So you're going to start here, and then you're going to go here, here, then you're going to go here, 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 here. You're just going to go kind of like that, okay? By just putting in the next position in the array, you're gonna, fill these guys up like that. And okay, that's the last position thing for a fully filled tree. Then, after you put it in the last position, you check to ensure the semantic property is still intact. That is, you compare the parent with both of its children to make sure that the parent is smaller than both its children. And if it isn't, you swap the parent with the swap parent with smallest child. And you do that all the way to top, if required, right? You might not have to go all the way to the top, but if you do a swap parent with child, then you've messed up the next parent potentially. So you may have to go to the top, but you can stop if you don't do a swap. So you insert the last position, and then you swap the parent with smallest child. Yeah. All the way to the top if necessary. So that swapping could take log n, because this is a binary tree and you're traveling from the bottom potentially all the way to the top, which for a binary tree, the height of the tree is log n, right? So one insertion operation takes log n, because you start at the bottom, and then you may have to go to the top. So worst case, it's log n. All right. There's another video on analyzing the time complexity of this thing. I talk a little bit more about that. But, okay, those are the rules. So let me just do an example here. So let's do a heap sort for this sequence. I'm going to do 3, 1, 4, 5, 2, 7, 6. Okay, because this is a fully filled tree, it's efficient to store it in an array. So here's our array. The index is on there. This will fit in a three-layer array, three-layer tree. So there's layer 1 here, and layer 2 is these 2 guys. Layer 3 has these 3 guys. So get started. So it's time to insert the 3. So the 3 goes here. Nothing to do because it's just one node. All right, then we insert the 1. So I forgot to put the 3 in here. There's the 3, all right? Then we do the 1. The 1 goes in the last position, which corresponds to this position in the tree. That's where you start. Then you ensure the semantic property by looking at the parent and making sure the parent is smaller than both its children. And if it isn't, you swap the parent with the smallest child. So the smallest child is 1 here, so I swap 1 and 3. All right, and just to redraw, here's our new tree. Okay, then we put 4 in there. So 4 goes in the next available position, so it goes here. And then you compare the parent with both its children, and it's smaller than both its children, so we're done. I'll redraw. Time to put in the, so this was insert 4. Let's insert 5 now. So the 5 goes in this next available position, which corresponds to this place in the array. This is actually where you're putting it in the implementation. You would just be using an array, and you'd stick it there, and you'd keep a count, right? And just put it there. Then you compare parent smaller than child. We're good. Time to do insert 2. So redrawing the tree real quick. So 2 goes in this next available position, which is here in the array. Then you compare the parent with both the children, and you swap with the smallest child. So the 2 goes here, and the 3 goes here. And then you keep comparing all the way until you don't have to do any swaps, right? So 1 is smaller than both his parents. We're good. So I had to swap 2 and 3. Okay? We can double check. Let me redraw real quick. We can double check. Well, let me redraw. So 1 is at the first layer, 2 and 4 are at the next layer, right? This is layer 1. This is layer 0. This is, layer 2. 2 and 4 are at the next layer. 5 and 3 are at the next layer. So we're good. So let's do insert 7. So the 7 goes in the next available position here, which would be here. 4 is smaller, so we're good. I'm going to go ahead and insert the 6 as well. So 6 goes in the next available position. It'd be here. The parent is smaller than both its children, so we're good. So we've filled the min heap. The semantic property is good. Let's check. 1 is smaller than 2 and 4. 2 is smaller than 5 and 3. 4 is smaller than 7 and 6, right? Just the only thing you care about semantically is that the parent is smaller than both his children. It's not like a search tree, right? A search tree has a slightly different rule than that. This is a min heap. And for a max heap, you would just make bigger on top, and it would be the same thing, just kind of inverted. All right, this was the insertions. Okay, it's time to we have to do deletions now. So because the smallest item is always at the top in a min heap, if every time you do an every time you do a deletion, you're removing the smallest item. So you're going to remove the 1, and then 2 will be at the top, and you'll remove the 2, and 3 will be at the top, and you'll remove the 3, and they'll come off in sorted order. So this was the insertions I did. let's do the deletions over here. The changes that happen for the deletions. So I'm going to redraw the tree. So 1, 2, 4, 5, 3, 7, 6. So to delete, you always replace the root with the last item. So the 6 comes up here and 1 comes down here. So I replace the 6 with a 1 and the 1 with a 6. So the 1 is now outside of the tree. It's not part of the tree anymore. It's part of the list, which is our answer. So 1 is our list, just 1. And everything else above is the tree. So first thing you do is swap the root with the last item. Then check your semantic property. Is the parent smaller than both its children? It's not. So I got to swap with the smallest child. So I swap the 2 and the 6. Okay. Then I compare again until there's no more swaps. The 3 is the smallest child, so I swap the 3 and the 6. Okay. And we came all the way down and we're done. So I'm going to redraw this thing because it's easy to get lost when you're doing this stuff. 2, 3, 4, 5, 6, 7. And yeah, that was deleting, this was deleting 1 right here. Both of these, this is delete, both of these guys was delete 1. You know, delete the 1. And we end up with this. Let me redraw because, you know, it gets so messy, right, with all these crazy things on here. So now we're gonna delete the 2, basically. So to delete the 2, which is the root, you swap the root with the last item in the list. So the 2 goes down here and the 7 comes up here. So we're swapping the 2 and the 7. Then we check the semantic property. 7 needs to be, we need to swap the 7 with the smallest child. So we swap the 7 and the 3. So the 7 and the 3 get swapped. And then we swap the 7 with its smallest child, the 5. So we swap the 7 and the 5. So now we're swapping 7 and 5. So now we're all the way down at the bottom. So I'm going to redraw the trees. 3, 5, 4, 7, 6. And let's just check that a couple of things. Is the semantic property good? Is this parent smaller than both its children? Yes. Is this parent smaller than both its children? Yes. Does it match my array? Is the 3's in layer 0, the 4 and the 5 are in layer 1, the 7 and the 6 are in layer 2, and the 1 and the 2 are in the answer now. They're in the sorted list that we're trying to generate. All right, so that was delete 2. Let's redraw this thing. 3, 5, 4, 7, 6, and it's time to delete the 3. So you swap the 3 with the last item in the list. So the 6 comes up here. So I swapped the 3 and the 6. So 6 comes up here. The 3 goes down here, and the 1, 2, 3 you see is the sorted part of the answer, the list. We're turning a tree into a list, kind of, if you want to think about it that way. Okay, so we do the swap. Then you compare the semantic property. Parent smaller than both the children. Got to put the 4 up here, right? Bring the smaller child up. So I swap the 4 and the 6. So the 4 and the I swap the, where's the 4? This one, 6. Then we're down to we've gone down here as far as 6 has no children, so there's nothing else to do. So we'll redraw 4, 5, 6, 7. Okay, that was delete 3. Then redrawing 4, 5, 6, 7. It's time to delete the 4. So once again, you always delete the root and you swap the root with the last item in the tree. So I swapped the 4 and the 7. So the 7's here and the 4's here. So essentially, you're removing the root each time and putting it into the list, right? I just removed the 4 from the root of the tree and put it into the next position in the sorted list. So I have 1, 2, 3, 4 in the list, and the rest of the remaining items are the tree. Then so first you do this, swap the root with the last item, then check the semantic property. So the 7 swaps with the 5 because 5 is the smallest of 7's 2 children, right? You swap the parent with the smallest child, with its smallest child. So in this case, that's the 5. And then you keep going. So now that we're done, that was because 4 is no longer in the tree. I shouldn't even put that on there because I shouldn't put it on the tree down here because it's confusing. That's what's messing me up. I really shouldn't put these things here. They're no longer in the tree. They're just, they're in the list now. But anyway, so just redrawing 5, 7, 6. Okay, so now delete the 5. So we have 5, 7, 6. Remove this guy, replace him with the last item in the list. So the 6 and the 5. Okay, and then 6 is smaller than 7. So redrawing, you have this thing. And the list is 1, 2, 3, 4, 5, and the tree is just 6 and 7. That was delete 5. Then it's time to delete, the root, which is 6. You're always deleting the root. In this case, the root is 6. You do that by swapping the root with the last item. So we're swapping 6 and 7. Wait. We're swapping 7 with 6 and 7 should have been. I think I skipped a swap somewhere in here. I think there should have been a 6. There should have been 5, 6. There should have been a 6 here and a 7 here. You swap the 6 and I'm not sure how I got there, but 7, the 6 would be here. I skipped something in here. So the tree is just 7 now, and then you delete, the 7. You swap it with itself. Swap 7 with 7, and no children to fix. So we're good. Okay, so we did. So that was it. So we did, what's the big O real quick? We did n insertions and n deletions. Each insertion took worst case log n, because in worst case, you would put the new item at the end of the tree, and then you may have to go all the way to the top of the tree doing swaps. And the height of the tree is log n. So worst case, you have to go log n all the way up. So there was n of those. So worst case, there was n log n of these guys. Same with deletions. You replace the last item with the root, and then worst case, you'd have to go all the way down, which is log n. So it would be n log n. So there's n log n insertions, n log n deletions, which you add those together. It would be 2 n log n, but we don't care about the 2, so we just we don't care about the constants in these things. We just care about the general shape of the curve. So it's n log n. Okay. Thank you.